Hi everyone, this is Bowen. I'm a PhD candidate at UIUC. Today I'm going to talk about my research work on image segmentation under the supervision of my advisor Alex Shreen. The title of this presentation is From Pixels to Regions Toward Universal Image Segmentation. Image segmentation is the task of grouping pixels into meaningful regions. Different image segmentation tasks have been proposed by clearly defining what is a meaningful region. For example, semantic segmentation groups pixels by their category membership. Instance segmentation groups pixels by their instance membership. And more recently, panoptic segmentation tries to unify both semantic and instance segmentation by grouping pixels with both category and instance membership. Although image segmentation is about grouping pixels, these different semantics for grouping pixels have led to specialized architectures. For semantic segmentation, per-pixel classification models are developed to predict a category label for every pixel. An example is the fully convolutional network, which converts any image classification model to a per-pixel classification model. By predicting the label of every pixel, the FCM model implicitly partitions the image into segments each associated with a different category. In contrast, instance segmentation usually follows a mask classification paradigm. Mask classification model first generates a set of n-binary masks per image. Unlike per-pixel classification, these masks are class agnostic, and the model is free to group pixels in any way, not limited to their semantic meaning. Then a mask classification model predicts a global category label for each of the n-binary masks, and all foreground pixels of a binary mask share the same predicted class label. Different from per-pixel classification model that is trained with a single per-pixel classification loss, the mask classification model usually requires two losses: a per-pixel binary mask loss to supervise the binary mask prediction, as shown by the red arrow, and the per-mask classification loss to supervise the per-mask classification, as shown by the purple arrow. An example is the mask RCM model that converts any object detector to a mask classification model. Although we observe these specialized architectures improve benchmark results on the semantic and instance segmentation tasks, they do not generalize to the other tasks. For example, an FCM model cannot be used for instance segmentation. This leads to duplicated research and engineering effort. Thus, we ask the question, does there exist a single architecture that can address any image segmentation task? In this presentation, I will refer the ability to address any image segmentation task as universal image segmentation. And the single architecture is named universal architecture. According to its formulation, mask classification is sufficiently general to solve both semantic and instance level segmentation. Moreover, mask classification is actually not new for semantic segmentation. It was once popular between 2010 and 2015, before FCM was introduced, and most state-of-the-art methods at that time were based on mask classification. Here I list some examples like O2P, RCNN, SDS, and CFM. So why not try mask classification for semantic segmentation again? In our work, per-pixel classification is not all you need for semantic segmentation. We explore the possibility of addressing semantic segmentation with a mask classification formulation. In this work, we propose MaskFormer, which is a model that can convert any per-pixel classification model to a mask classification model. MaskFormer starts with a pixel-level module, which consists of a backbone to extract image features, usually of low resolution, and a pixel decoder to recover high-resolution features. Note that any existing per-pixel classification model can be used here. Then we use a transformer decoder to extract n-query features from image features, denoted as Q in this figure. We follow the design of DITR, where we use n-learnable queries in the transformer decoder, and each query corresponds to a segment. We apply a linear classifier to predict one of the k category labels for each of the n segments. We also add an additional no-object category in case the embedding does not correspond to any region. Hence, there are k+1 options in the classifier. The detailed model is interested in object detection, so it applies an MLP on query features to predict n bounding boxes. However, we are interested in predicting the mask instead. So instead of predicting bounding boxes, we apply an MLP on these n query features to generate n mask embeddings of the same dimension as per pixel embeddings. To decode binary masks, we simply perform a dot product between mask embeddings and per pixel embeddings, followed by a sigmoid activation. Since our mask prediction does not require predicting bounding boxes, the MaskFormer is essentially a box-free version of DITR. The combination of class predictions and binary mask predictions already gives us output for instance segmentation and panoptic segmentation. What about semantic segmentation? We design a simple inference strategy for semantic segmentation. The final prediction is obtained by a dot product between per second class probability predictions and per second mask predictions. We drop the no-object category since semantic segmentation requires a prediction for every pixel. So how well does MaskFormer perform in practice? I will present the comparison with state-of-the-art methods on both semantic segmentation and panoptic segmentation tasks. We first compare MaskFormer with state-of-the-art DeepLab Research Plus on the ADE20K dataset for semantic segmentation with a standard CNN backbone, which is a ResNet 101C. MaskFormer outperforms DeepLab Research Plus by 1.6 MLU while being more efficient. This is because that although we add additional transformer layers to a per pixel module, MaskFormer removes the need for heavy context aggregation mechanisms like ASPP or heavy pixel decoder like Atrus convolution. Our MaskFormer is also compatible with recent transformer backbones. For instance, with a swing large backbone, the MaskFormer achieves new state-of-the-art performance of 55.6 MLU while requiring fewer flops and while being faster. In summary, our MaskFormer sets new state-of-the-art on semantic segmentation while having smaller model size and being more efficient. Next, we compare MaskFormer with state-of-the-art models on COCO for the panoptic segmentation task. Since MaskFormer is a box-free version of DITR, we begin with comparing our model with DITR using the same CNN backbone, which is ResNet 101. We showed that removing the dependency on box predictions improves the performance by 2.5 PQ. We hypothesize this is because representing stuff with bounding boxes is very ambiguous. And this also explains why existing mask classification models like MaskCarCN may not work well for semantic segmentation, as they usually depend on box prediction. We also compare MaskFormer with the more recent MaxDeepLab model using transformer backbones. MaskFormer outperforms MaxDeepLab by 1.6 PQ while being half in model size and quarter in flops. Moreover, although MaxDeepLab is also box-free, it requires multiple extra auxiliary losses besides the final mask loss, whereas MaskFormer is simpler as it only requires a single mask loss. And we can train it with the exact same losses, architecture, and training pipeline on panoptic segmentation as on semantic segmentation. We also compare MaskFormer with per pixel baseline plus, which is a per pixel classification model having the exact same architecture as MaskFormer, but uses a per pixel classification paradigm. We observe that as the number of categories increases, our MaskFormer's improvements over the per pixel classification model becomes larger. This suggests that a single class prediction per mask may model fine-grained recognition better. With these experiments, we conclude that mask classification is indeed sufficiently general for both semantic and instance-level segmentation. More importantly, it also gives answer to the question whether mask classification is better for semantic segmentation. And the answer is yes, as MaskFormer shows new state-of-the-art performance. As we aimed for earlier, we want a single architecture for any image segmentation task. Now a new question naturally emerges. Are current mask classification models good enough to unify different segmentation tasks and even replace those specialized architectures? To answer this question, We begin with comparing MaskFormer with state-of-the-art specialized architectures on 3 image segmentation tasks. Unfortunately, although MaskFormer works well for panoptic and semantic segmentation, it still lags behind specialized architectures on the instance segmentation task. So what are the limitations and how can we improve it? The strong performance on panoptic segmentation and semantic segmentation suggests that the meta-architecture of MaskFormer seems to work well, which consists of a backbone, a pixel decoder, and a transformer decoder. As backbone and pixel decoder designs have been widely explored for a long time, we believe issues are with the transformer decoder, which has not been introduced to image segmentation until recently. For example, with the standard transformer decoder, the model converges slowly. Training a MaskFormer model takes 10 times more iterations than a MaskRCN-based model. This is due to cross-attention attending to the whole image feature map, and recent work shows it takes long iterations to train the cross-attention to attend to local regions. Another issue is about poor small object results, and we believe this is because we are only using a single low-resolution feature map to segment objects. We try to address these aforementioned issues of MaskFormer in a recent work named Mask Attention Mask Transformer for Universal Image Segmentation. To address the slow convergence, we replaced the standard cross-attention as shown on the left with mask attention as shown on the right. The mask attention extracts localized features by setting attention weights on the background to negative infinity before applying the softmax. And we choose background regions based on the mask predictions from the previous layer. To improve small object results, we propose to use multi-scale high-resolution features. Compared to the original MaskFormer on the left that only uses a single low-resolution feature map, we feed different resolutions of feature map to different decoder layers as shown on the right. With these proposed changes, our MaskFormer can achieve new state-of-the-art on all 3 image segmentation tasks with a single unified architecture. More importantly, MaskFormer generalizes to different datasets as well. Here we compare our MaskFormer shown in the orange bar with specialized architecture for each particular task and dataset shown in the blue bar. On COCO, MaskFormer outperforms specialized architectures on both panoptic and instance segmentation. On cityscapes, a single MaskFormer architecture is enough for all 3 tasks. And we observe similarly for ADE20K and Mapillary Vistas. These results show that MaskFormer's ability to serve as a universal architecture. In conclusion, I believe a mask classification model can address any image segmentation task. But what's next? You may not realize that image segmentation is important because it serves as the core algorithm for many applications, and it has been used everywhere. For example, video conferencing has become part of our life since we started working remotely. One of the key features in these video conferencing tools like Zoom or Google Meet is the virtual background. In order to change the background, we need to separate the person from the background, and this is achieved by a segmentation model as shown on the right example. Image segmentation is also used in the camera of your smartphone. For example, Apple uses person segmentation to power the portrait mode, as well as many other image enhancement applications. More recently, there is an increasing interest in self-driving cars, and Tesla is currently trying to use image segmentation to help collect labels to train models for full self-driving. So, beyond image segmentation itself, I'm also interested in studying how to better use image segmentation to help other tasks as well. In summary, in this presentation, I started with universal image segmentation, where my goal is to find a single architecture that can address multiple image segmentation tasks. I found mask classification is the right way to go and showed that mask classification can successfully address multiple image segmentation tasks. Beyond image segmentation, I think it is important to study how to use image segmentation to help other tasks or applications. And that's all from my side. Thank you.